Today we're going to talk about the evolution of antenna technology, past, present, and future. Some highlights. I have a lot of slides. We're going to go pretty fast. I think we only have about 45 minutes, although people, they give me a couple of hours anyway, so we can change the schedule as we go along. According to John Krause, who was a pioneer in antenna technology, some of you may be familiar with his textbook, which was published in 1950. It says the antennas are the eyes and ears of a wireless communication system. Just like the eyes and ears to a human being, same thing for the antennas to the wireless communication. So if the antennas, if your eyes and ears don't work very well, you're not very effective. Well, same thing with the wireless communication system. If the antenna doesn't work well, no matter how good the communication system is, it will not work. It will not be able to transmit and receive signals, messages efficiently. So very important. So today, we want to talk a little bit about how all this technology got started, present, and maybe some suggestions about the future of antenna technology. The past, we're going to memory lane, we're going to outline some time periods, some of the significant developments of antenna technology. And we go back really to Hertz in the 1800s, which was the genesis of radio and antenna engineering. So in 1980s, late 1980s, 86, 87 time period, Hertz put together a wireless communication system where we had a transmitting antenna, a dipole, very simple. Nearby had a loop antenna, rectangular in shape, and to the dipole, transmitting dipole, he connected an induction coil, and then he induced a voltage on the induction coil, which created a spark at the feed points of the transmitting dipole, and that in turn created a spark in the receiving antenna. So this was, again, the genesis of transmitting and receiving signals wirelessly. Then the other one, of course, we all heard about Marconi, going back to the early 1900s, in particular around December 1901, where he transmitted a signal from Cornwall, England to Newfoundland, Canada. And this was the genesis of long distance wireless communication. Now, modern technology, antenna technology, really got started in the 1920s. This was probably one of the most well-known antenna system, Yagi-Uda antenna. A lot of the ham radio operators, they call it the Yagi, and that's a misnomer. Really, it should be the Yagi-Uda. What happened here, it was Yagi and Uda were colleagues in Japan. And Yagi came to the United States in 1920s. He was invited by what is now IEEE. It used to be IRE, the Institute of Radio Engineers. That in 1963 is when we transitioned from IRE to the IEEE. And he presented a paper in a convention of IRE. It was Yagi. Only he was the author, and that's what a lot of people say, the Yagi antenna. That's a misnomer, and I don't think it gives credit to his colleague, Uda. So you can see when Yagi in the 1800s to early 1900s, and here's his colleague, Uda. So that was the genesis of modern antenna technology. Now, the Yagi was used for TV, but it was kind of narrow band, only for a few channels, back in the old days, we'll talk about here. But here's what the configuration, about an array of dipoles. So we have one element which is energized. Okay, that's the feed element, whether you're transmitting or receiving. Then you have a reflector, which kind of pushes the energy in the right, to the right, I should say. And you can use one or two at the very most. And then you have what we refer to as the directors. They're the ones that kind of direct the energy in the forward direction to the right. And create a pattern as shown here. Now the applications, as I already mentioned a little bit, amateur radio, TV antenna, but narrowband, but high gain. We'll compare with another very popular TV antenna in a few minutes. And then frequency ranges, HF, VHF, UHF, those were the frequency ranges. Because it's so popular, so well known, I'm giving you kind of one of the initial designs. Okay, it's not necessarily the most optimized design. People have since then have optimized the characteristics. Typically, the feed element is slightly less than a half a wavelength to be, in order to be resonant. Okay, a dipole, for example, half a wavelength, you make it a little less than a half a wavelength, it becomes resonant. The reflector is slightly greater than the feed element, slightly greater than a half a wavelength. Reflector or reflectors, as I said, no more than about 2 necessary. The directors, slightly less than a half a wavelength. About 4/10 to 0.45 wavelengths, and then spacing, very critical. And what I'm showing here, all those are fixed lengths, fixed separations. To optimize them, you can make them variable, okay? And people have done that. But this is one of the initial director spacing, somewhere between 0.3, 0.4 wavelengths. Again, as I indicated, if you want to optimize the performance, you can vary all those special nowadays with software and things like that. You can optimize you can get another couple of dB in directivity and gain and so forth. So that's one of the initial designs. And here's a typical pattern, as I'm showing over here. This is about 15 elements, about directivity, about 15 dB. And those are the E-plane and H-plane beam widths in the E-plane and in the H-plane. Okay, now here's commercial Yayuda antenna. This is for, obviously not too many people use them today. Everybody uses cable and accommodate many more channels. Back in the older days, some of you were not around. Some of us been around for a long time. We had a channels 2 through 13. Channel 2 about 54 megahertz. Channel 13 about 216 megahertz. And this kind of design was a Weingart company could accommodate the reception for those TV channels decades ago. Okay. Whoops, I think I did. So here are kind of the gain for channel 2 and for channel 13. As I indicated, the YAG antenna got a lot of publicity. In 1984, IEEE published in the Proceedings of the IEEE, which is the journal for all areas of electrical engineering, because IEEE has 39 journals in the different areas of electrical engineering. That's how many societies that we have within IEEE. Okay, antenna propagation is one of them. You have, signal processing, communication, power, biomedical. 39 societies, 39 journals and transactions. Well, in the Proceedings of the IEEE is for all societies. So in 1984, they celebrated the 100-year anniversary. They published some of the key and well-known papers in each of the areas of electrical engineering. In Antennas of Propagation, they published only one, the paper by Yagi in 1928. And this was the initial publication when Yagi came to the United States to present the initial paper. Okay, but he didn't put the name of his colleague. It was only his name. That's why people, they call it the Yagi. Okay, and then let me go over here back again. So you can see the third one there, or the second, I should say, Proceedings of the IEEE 1984. That's a paper that it was published in the Proceedings. Not only that, in 1997, they repeated. They republished that in its original form, the way it was in 1928. So that's how classic of paper it was, and still is, by the way. Okay, another well-known antenna is the helical antenna, or the helix, as some people refer to. This is attributed to Professor John Krause from The Ohio State University. Got to say The Ohio State University. Otherwise, alumni from there, well, I guess I'm one of them. John Krause, a great person, a gentleman. On the top of that, I had the pleasure to meet him, to host him. Came up with the helical antenna, and here's kind of the configuration, the dimensions. I'm not going to spend too much time because we're going to run out of time. It was published initially in 1947. Now here it has two basic modes. If the circumference of the turns of the helical antenna are smaller than one wavelength, okay, you get what they call the broadside mode. It's like this one here. It's like a dipole has. Okay, the maximum is broadside, as I'm showing here. That's referred to as the normal or the broadside mode. But if you make it to around one wavelength in circumference, you get the axial or the end-fire mode, where the maximum is along this direction over here. Very popular, again, even in the space program. I had pleasure to work for NASA back in the 60s in one of the tracking stations in Virginia. I think they used to use helical antennas to communicate with the astronauts. Okay, or here's a commercial helical antenna by courtesy of CV Engineering Associates. Now this is the other one, popular TV antenna, log periodic antenna. This was attributed primarily to the people from the University of Illinois. That's what Duhamel and Isbell, they were on the staff, on the faculty of University of Illinois in Urbana, Illinois. Now, this is kind of the configuration that what the lengths, the separations between the elements, the diameters, if you really want to go, of the wires, they're all variable. They're not the same, okay? But they all change by the same ratio, as well as the separations at the feed point. Well, this kind of an antenna creates a beam in this direction over here. That's the log periodic. Now, you're going to say, why they call it log periodic? What does it mean? Well, let me show you here in a minute. Here is how the lengths of the elements vary. Those are the separations. Those are the diameters of the wires. This is an ideal design. The variation of the diameter of the wires is not that critical. But the lengths are, the separations are, and ultimately even the gap spacing at the feed point of each one of the dipoles should vary accordingly. But that's, again, not that important, that critical, I should say. And they all vary by the same ratio. Okay. Now, if you were to plot the input impedance of this one, is periodic. It varies periodically. And you can see here that this is the period. but it's periodic if you plot it as a function not of the frequency, of the log of the frequency. Hence the name what? Logarithmic periodic. That's what log periodic stands for, logarithmic periodic, because the period varies, repeats itself, it's constant as a function if you of the log of the frequency, not of the frequency. Okay. So hence the name, log periodic. Here's a typical variation of the pattern. We talked about the channels 2 through 13 back in older days. The gain, I think, is about 7 dB. And be able to accommodate both the channel 2 and all the way up to channel 13. You can see the gain kind of stays flat, constant over that frequency range. And just to compare, I mentioned Yagi-Uda antenna was also used as a TV antenna, but the log periodic is much broadband compared to the Yagi antenna. On the contrast, though, the gain or the directivity of the Yagi is much higher, like in this case 15 dB versus about 7 dB for the log periodic antenna. So log periodic, more broadband, lower gain. The Yagi antenna, Yagi-Uda antenna, more narrowband but higher gain. That's what you compare. Okay, the trade-offs between the two of them. Here's a commercial log periodic antenna, and most of the TV antennas were log periodic eventually. All right, now microwave antenna technology. Actually, most of people think it started more during this space program, but I'll give you a little history on that, which goes back even to the days of Hertz in the 1800s, actually. But you can read a lot of this, you can find a lot of the history of an evolution of antenna technology in the book by Silver. This was part of the MIT radiation lab. They had like 30-some books in all areas of electrical engineering that were published. They were developed during World War II. They were kind of classified during that period and then eventually became open to the public. There were, I think, like almost 30-some books. One of them was in the microwave antenna technology, edited by Samuel Silver. So this was the genesis of microwave antenna technology. Of course, it became very popular during the space program, if you remember that. But if you go back, though, even during the day of Hertz, he created a cylindrical reflector, which was only curved in one plane. Okay, that's what we usually refer to as a cylindrical reflector. In 1988, was it 87, 88 time period. Then later on, in Wheaton, Illinois, there was a gentleman, Reber. He was more of an astronomer. He was also ham radio operator. He built a parabolic reflector, as I'm showing you over here. So you can see that was about 1938. And by the way, 1938, a lot of good things happened. I'll let you, I'll give you something to think about. What else happened in 1938? You're looking at me. I had him in class, and he doesn't know it. He says, what really happened? He never told us that. All right. Now, of course, this is the reflector at Goldstone, California, where it was used, for the space program. It was a 70-meter, about 210-foot diameter reflector. Very popular. In fact, even on the 4th edition of an antenna book, I got permission, obviously, to use it on the cover. That's what we have on the cover of that one. Another very popular microwave antenna is the horn antenna. Now, I think all of us have used it numerous times. I'm showing you only the pyramidal one. There's also a conical one. And this one goes back, again, the inventor, it goes back to 1938. What did I say about 1938? Something happened, right? It was a good year. And this was, I think, invented 38. I think he got patent in 1949. Very popular. I'm not going to spend too much time, again, because of time limitations. What the pattern looks like, three-dimensional. This is the kind of a pattern. Again, I'm trying to publicize the book. Now, in other words, the patterns in the fourth edition, they're in color. Okay, they were in the fourth edition. And this is one of the figures, from the chapter on horn antenna. So you can see three-dimensional variation of the pattern of horn antenna, pyramidal horn antenna, the dimensions, and so forth. And this one has a gain of about 18 dB. Typically, horn antenna, 15 to 25 dB, somewhere in there. The microwave antennas, microwave horn antennas, somewhere in that range. So this one that we simulated and turns out to be about 19 dB. Here's a commercial one. This had a gain of about 16 dB. This is what we call exponentially tapered. In other words, the transition from the waveguide, the feed point, to the aperture, radiating aperture, is smoothly varying in an exponential manner. There were no discontinuities. Provides much better transition, and you can get a VSWR close to unity, really. If you measure it, 1.01 or something, 1.05, you know what I'm talking about? Almost a perfect match. Microstrip antenna, very, very popular. Basically in the 60s, in the 70s, and some of us lived through this transition period. However, actually, the introduction goes much earlier, and I'll show you that in a minute. You can have a microstrip antenna where the patch is kind of rectangular in shape, or you can have one which the patch is circular in shape, as I'm showing here. Actually, the inventor of this one was George Deschamps, University of Illinois. And this was back in 1953. But he stayed dormant for almost at least 10, 15 years. 1960s, I remember when I used to work for NASA during that time, it was microstrip antenna. But it was actually popularized even more in the 70s. There's another gentleman, Bob Munson. Okay? He's the one published a paper in 1974. And so that's what the microstrip, what people used to a lot of times refer to as the patch antenna. Very popular. He has a lot of attractive characteristics. Here, I'm listing some of them. Low profile, very simple to construct. Okay? Versatile, mechanically robust. Versatile in terms of polarization and resonant frequency. Very easy. Here's a photograph of a 10 by 10. This is courtesy of Ball Aerospace. That's what Bob Munson, that I just referred his name, he worked for. They in Colorado somewhere, they outside the Denver area. Oops, here we go again. All right, next. Now, I know some of you use, I'm told you use the dipoles, biconical antenna. So I put a little bit of information here concerning those just to show you some of them. So the bandwidth of an antenna like a dipole or biconical type of antenna, you can optimize if you can utilize the available space that surrounds that particular antenna. I'll show you here in a minute what I mean by that. So if we can go, for example, to just the classic dipole, which is shown over here, just a plain wire. Now, we have a sphere that encloses that dipole, but just a wire antenna doesn't take much of the space. It doesn't utilize much of the available space. So it's not a very broadband. Now, we can make it more broadband if we go to what? By a conical antenna. By conical antenna, it takes more of the space within of the sphere, which it surrounds. Okay? But again, we have to truncate it. So, you know, the VSWR may not be as good if you have a smooth tapering transition, I think, from the feed towards the ends of the biconical antenna. So as we go from one to the next one, the bandwidth goes what? Up. Ultimately, even though this maybe not used as much, you can use 2 half spheres. Takes all the space available within the volume of a sphere that encloses the element. So that's one way of increasing the bandwidth of the antenna. Now, you can also, of course, you can simulate and actually build it. For example, if you want to mount it, I think, on a pole or somewhere, for example, a bonic antenna, if it's solid surface, wind resistance, it may be a problem for you. You know, it may be swaying instead of maybe moving. Well, you can approximate a biconical with the wires, as I'm showing over here. And how many of them you use, that's how close to the solid surface it would be. People have done that. Okay. That's one way to minimize the weight, the wind resistance, if you wish, of the antenna. Bow tie, if you take a slice of a biconical antenna, that's very popular, as you can see here. And of course, feeding them, you use what they call balun. Some people call it balloon, but it's actually balun, balanced, unbalanced, because the element itself is a balanced element, and if you use a coaxial line, the coaxial line is an unbalanced line. So to connect the two, provide transition but from a balanced element to unbalanced line, you use this device which we call balun, balanced, unbalanced, okay? Very popular. Now here's if you were to compare a solid biconical antenna with a bow tie, a bow tie with simulation and measurements. You look at the S11, which is basically the reflection coefficient, if you wish. And you can see how well those two, compare, measurements versus simulations. Now here's kind of, if you were to, especially with today's software, you can see where the current density is the maximum, is along the edges. The center part of the bow tie antenna is not that critical. So actually you can remove it, and without really altering that much of the radiation characteristics. And I'll show you that in a minute. Now, here is the solid one, and we can go remove. I'm just showing you, for comparison. The one on the left, you can see where the current density, where it's red. That's where the most intense current density is. So we remove, let's say, if we were to remove the center part and compare one where we have removed the center part versus the solid one to see how well they compare. And here they are. This would be the one where we have removed the center part of it. We call it maybe the outline. The outline would be just a wire type of a bow tie. And here we compare the two of them. The black one is the wire type. The red one is a solid one. So we're plotting the S11 versus frequency, and you can see the difference. Yes, the outline one resonates at a lower frequency because it looks bigger. You know what I mean? Compared to the solid one, electrically it looks bigger, and that's why it resonates. Physically, it looks bigger and resonates at a lower frequency. Another one is, and we had worked with a local company over here. They had a specific type of a substrate, flexible. There is, it's actually a research center of ASU. They're called Flexible Display Center. It's in South Tempe. And they had a particular flexible substrate. They call it PEN, P-E-N, stands for polyethylene naphthalate. We worked closely with them, and they gave us some of that. We built one, as you can see here, that we can bend it. Okay? And actually, this was published in a paper, I think, in 2011 in the IEEE Transactions on Antennas and Propagation. There's a lot more information that we had on that. But anyway, another apparently popular antenna, Vivaldi, I think you guys were talking about, somebody communicated with. Again, this is a slot antenna with a smooth transition, exponential transition, provides a good match, if you wish, from the connector, the connecting transmission line to the element itself. And this is kind of, the first one is kind of a three-dimensional view. The other one is the top view. And of course, the other one is the side view, as we can see. And you can see this, we're plotting the current density on it. You can see the most intense current density is in the transition from, let's say, the feeding transmission line to the aperture of the antenna. Folded dipole, another one for FM broadcast TV antenna. Let's see here. Back in the old days, again, you know, we have array of dipoles. Okay, then we have the TV. The TV wants to 300 ohms. Okay. Now, if we use a cable you typically, let's say, as an approximation, let's say 75 ohms. But the TV wants to see 300 ohms. So we have to use what? Impedance transformer, 4-to-1, to provide the match. However, if you use a folded dipole, instead of using just a regular linear dipole, you use like a very thin rectangular loop, basically. Okay, that's what we call a folded dipole. Well, now then, and we use a twin lead line. Twin lead line is a 300 ohm line, approximately. And you can see that we can adjust the dimensions of the folded dipole to provide a perfect match, or provide an input impedance of about 300 ohms to match the transmission line. And here it is, and I'm not going to go through a lot of the details, but this one here shows you a particular design using the dimensions, the diameter, and the spacing of the folded dipole, that you can get an input impedance of 300 ohms. And now you can, this is kind of the equivalent circuit, you know, of the, if you have just a regular dipole, and then of course, if you make a folded dipole, it's like you have an impedance transformer, as we're showing over here, like a 2-to-1 ratio. And then you can put everything, bring everything to the input side of it. And basically, you get a 4-to-1. I mentioned the 4-to-1 impedance ratio. So when you make the length of the folded dipole exactly half a wavelength, the input impedance is 4 times the impedance of the dipole. If the dipole is 75 ohms, 4-to-1, it would give you 300 ohms, perfect match for a 300 ohm line. So today, what are we doing? Well, there are a lot of things happening. As I'll just give you some of the things that are happening. Also, some things that we have done here, at ASU. I've been, as I indicated, I retired a couple of years ago. And it was the 37.5 years at ASU. Okay, we built a facility. Now we'll show you that towards the end. Multiband antennas. Nowadays, we have so many different systems that we want to connect with, and you cannot build an antenna for each system that, let's say, you have a mobile device like a cell phone to accommodate everything that we want to receive information from. So can we design an element which is multiband? And the answer is yes. Let's take an example, simple example. I mentioned the microstrip antenna, very popular, very versatile. Okay, so here we've shown you initially, you can see this thing flashing, one frequency. You adjust the dimensions of the patch to accommodate a frequency. Now we want another frequency. Are we going to introduce another patch? The answer, no. We can use the same patch and put a slot. Okay? And this slot will accommodate the second frequency. Then you can put another slot. Okay? Now you can't just go cut slots. You got to do them properly because they become interference. In fact, we had a current density. We have more information because, again, time limitations. I'm not going to go through it. But anyway, you can do something like this. Here is using the same patch, same physical dimensions, but accommodating 3 frequencies. Now you say, well, that's just simulations. No, actually, people build one. Here's one, for example. You can see the slot. This was for GSM, first generation communication system. And the second slot there is for DCS, digital communication system. Okay, so the same physical dimensions, but accommodating 2 different frequency ranges. So you got to be creative. Okay, how to do that, how to minimize the number of elements that you need, let's say, to use to accommodate what your system wanted to do. Nowadays, I don't know, some of you may have heard about it. They say metasurfaces. What are metasurfaces? Well, those are surfaces which does not exist in nature, but we can actually synthesize such surfaces. I'll show you that. Meta is a Greek word that means beyond. Okay, beyond. It was introduced again by a professor at University of Texas at Austin. Gave the name, came up with the name, metasurfaces. Very popular nowadays. Not only popular, there's a lot of activity. In some societies, like the antenna propagation society, if you're not working in kind of metasurface related technology, you're not doing anything. In other words, you're falling asleep. Okay, so it's very popular. If you look at the transactions and some of the conferences, you will see a lot of papers, sessions related to metasurfaces. Now, what are they? Why and why we need them? For example, a dipole, horizontal dipole. If you put it above a metallic surface, by the way, PEC stands for perfect electric conductor. Perfect conductor, okay? Well, conductivity is infinity. You understand what I'm saying? Metal is a good approximation to it. Conductivity, 5.7 times 10 to the 7 Siemens per meter, for example. A very, very good conductor, for example. The height, if the height of the element above that surface is small, it becomes very inefficient. In fact, if you make the height 0, the thing doesn't radiate. Wow. Remember, we use the image to take into account, the presence of the plate, and the image is in the opposite direction. So whatever you get radiation from the actual element, the one in which is reflected from the surface is what? Equal and opposite. They cancel each other out. So 0 radiation. It shorts out, to put it in simple words. So what you need is PMC, perfect magnetic conductor, where the tangential in the PEC, the tangential components of the electric field vanish in boundary conditions. In the PMC, the tangential components of the H field vanish. So in this one, you can bring the element right on this surface to create a conformal type of a configuration, like for, let's say, flying platform. You don't want something sticking out and then creates drag and so forth. You want it to be conformal. But we don't have PMC surfaces. Yes, we do not have. We do have. We can synthesize them. Here's one of the first popular such a surface. So what do we have with a regular substrate? Well, we have the conductor with the, here's the ground plane. We have the dielectric layer. And then we have, we put patches on the top of a substrate. And then we connected the patches to the ground plane using vias. Well, this kind of a surface emulates, approximates a PMC surface. You say, how do you know? Well, we have to prove it, obviously. And here is, if we plot the phase of the deflection coefficient versus frequency, and this is actually simulations using a very popular software, HFSS, and some design equations and so forth. Yeah, there is a frequency range over this surface acts like PMC. It's actually an ideal PMC only in one frequency, but there's a bandwidth over, it's very close to a PMC surface, and that's a bandwidth over there. So where the phase of the reflection coefficient varies between plus 90 degrees to minus 90 degrees, and for this particular surface is from about 10.35 gigahertz to 14.25 gigahertz. That's it, where the phase variation is between plus 9 to minus 9. And exactly at the center there, which is about 12 gigahertz, the phase is 0. It's a perfect magnetic conductor. So it simulates, it synthesizes. This is synthesized surface to represent a PMC surface. Now we can put what? A dipole on top of it. Of course, because we have the metallic patches, we can't put them directly on top of them. We got to put some kind of a very thin dielectric layer on there, so the contact won't be there. We have done this. We have built and measured and so forth. All right. So this meta surface, when they interact with, I think we're getting close to we can get very unique and intriguing characteristics. Okay, I'm going to go to applications on the antennas. Here is, for example, I'm going to show you, this is a synthesized PMC surface over here. So we have a loop antenna, but this is circular instead of being rectangular. Here's a loop antenna there on the top of the surface. We actually build one of them. This is work we've done here, my group here at ASU. Simulations, measurement, we got a 3 dB increase in the gain of the antenna. Okay, then now we used another one. We got another dB and a half. This is the one I just finished showing you. And then we put a PSC collar around it. Metallic, color over here, and it looks like this. The center part is the one like the one I showed you a while ago. This is, we got another dB and a half, 10.5 instead of 9. So they are very, very, very popular, and they have attractive characteristics. Another one is application in visibility to the radar, provide low visibility, low RCS, radar cross-section as we refer to it. Okay, that's the parameter that we try to minimize, okay, which represents the visibility of a target to the radar. Okay, we'll be finishing here in a minute. Okay, so if we take a plate, this is basic electromagnetics. If we illuminate it in the side like this, most of the energy goes. at an angle where the angle of reflection is equal to the angle of incidence. Snell's law of reflection, as we refer to. Okay, so if you take a flat surface and you illuminate it vertically, where do you expect most of the energy to go? Towards you, towards the direction of the incident field. So this is very highly what? Visible. Ideally, all of it would go in that direction if the plate is infinite. But if we make it finite, you get this kind of a scattering pattern, as we refer to. What I talked about, these surfaces, meta-surfaces. If we take the same ground plane, you put patches on top of a different configuration. Okay, we're creating what we refer to as checkerboard type of a surface. You eliminate this surface, different patches. Now again, there's a lot of work, a lot of it that goes behind it. If we illuminate this one perpendicular, guess what? The energy goes in different directions. We're creating 4 lobes away from the direction of where the energy came from. We have lowered the visibility of this surface to the radar. Okay? How is this happening? When you illuminate this surface here with an electromagnetic wave, we're creating current densities on those patches. And the current density is different depending on the patches, how they design. We create an array of patches. We use an array theory from antenna technology, and that's how we control the scattering, not only create, but direct it away from the receiver. Here's another one, which is hexagon. This creates a pattern 6 lobes instead of 4 lobes like the previous one. Okay, so future. Integration of this, a lot of devices with the meta surface creates a lot of interesting work for the future. 5G communication, flexible antenna, reconfigurable, all kinds of ultra wideband, wearable, reflector arrays, terahertz antennas, and so there is, as a conclusion, there is today's antenna technology. You know, it used to be back in the old days, you had a TV antenna, you go over there and screw around with it and try to fix it. You know what I'm talking about? Not today. Today is a science, is not an art, if you wish. There's very, very bright future, many challenges. What do we need? We need to, excuse me, to exercise creativity, imagination, science, and so forth. So, obviously, I highly recommend, well, I should. I worked for the damn thing for 56 and a half years. No, if I don't know when else I'm going to do it. This is a facility that we built here. We got this young man over here. Again, I retired about a couple of years ago. They're using the facility. He's more in the communications area, but we have people also in electromagnetics antennas. They're using it. This was state-of-the-art facility. It was built about mid-1980s, about 85. It's 37 feet in length, about 25 feet in width, 18 feet in height. State-of-the-art. We have a compact range and so forth. It was one of the top 2 such facilities at a university. The only other one at that time was the one at Ohio State University, but they were, you know, in business since the 1950s. Okay, so here I are. If you want to know a little bit more about my background, what I have done, why antennas, why electromagnetics, if you go to the internet, you put Legends of Electromagnetics. This is just, I was interviewed about a month ago, a little over a month ago. You can go over there, you can, if you have a hard trouble sleeping, this would definitely put you to sleep. It's about 72 minutes, so I'm trying to publicize, you understand? Okay. You don't have to use the link. You can go just put Legends of Electromagnetics. We'll get you there. Thank you very much, and I'm happy to, whatever time we have, to entertain some questions. Thank you again.